Good morning, students. Today we will solve one numerical problem on vapor compression refrigeration cycle. The problem statement: consider an ideal refrigeration cycle that uses R134A as the working fluid. The temperature of the refrigerant in the evaporator is minus 20 degrees centigrade and in the condenser it is 40 degrees centigrade. The refrigerant is circulated at the rate of 0.03 kg per second. Determine the COP and the capacity of the plant in rate of refrigeration. Now, this is the schematic diagram of the refrigeration system. The left hand side is the schematic diagram of the refrigeration system, and the right hand diagram is the thermodynamic diagram. Here we have drawn the TS diagram. Now in the refrigeration system, as we know that there are four components: the evaporator, where the heat is absorbed from the refrigerated space or the cold space. That is the most important part. Now after that we have the compressor. So here we have from 4 to 1, we have the evaporation process where heat is absorbed from the refrigerated space. After that 1 to 2 is isentropic compression. In the isentropic compression, the the work is supplied to the compressor so that the pressure can be increased from 1 to 2, that is from the evaporator pressure up to the condenser pressure. This is the condensation process from 2 to 3, where heat is released to the surrounding. So this is QL, this is QH, and this is W in. As we know, the refrigeration cycle diagram. This is the refrigeration cycle diagram. This is TH. This is TL or TC, and we have work input to the refrigerator, actually to the compressor. So we can compare this cycle with this thermodynamic diagram as well as to the schematic diagram of the cycle. So this is the evaporator, this is the compressor, this is the condenser from 2 to 3, and from 3 to 4 the objective is to pressure drop from condenser pressure to the evaporator pressure, that is done by the expansion valve or the capillary tube. So these are the four components of the refrigeration system and corresponding TS diagram. So for the calculation of the COP, we know that COP is the desired effect by energy that costs. Desired effect for the refrigeration system is QL, and energy that cost is W in, and that is mass flow rate, or you can write rate of heat heat absorption divided by rate of work input. So it will be m dot into small ql by m dot into W in. This is small ql is the heat absorbed per unit mass of the working fluid, that is refrigerant, and W in is the work input to the compressor per unit mass of the refrigerant. So finally what we have to determine is QL by W in. Now what is QL? QL here is, this is state 1 and this is state 4, so QL will be simply H1 minus H4, and W in is, this is the compression process, so W in will be final enthalpy H2 minus initial enthalpy H1. So this quantity we have to determine, therefore we have to determine H1, H4, H2. Now we will see the conservation equations. All these are control volumes. All the essential components are control volumes. Therefore, we have to write the continuity equation, that is the mass conservation equation as well as the energy conservation equation. So continuity equation means for all the control volumes, there is only one inlet and one exit. Therefore, and they are steady flow devices. Therefore, inlet mass flow rate m dot I is equal to outlet mass flow rate, that is m dot E. We have assumed that is equal to m dot. Energy equation in the rate basis, Q dot Cv plus m dot into Hi plus Vi square by 2 plus the potential energy Gzi equal to m dot enthalpy at the exit, kinetic energy per unit mass at the exit plus potential energy per unit mass at the exit plus the work produced by the control volume. Now after rearrangement, that is division by m dot, we get the energy equation per unit mass, that is Q small q plus Hi plus Vi square by 2 plus Gzi is He V square by 2 plus Gze plus small w, that you already know. This is just for the recapitulation. Now this is small q is Q dot Cv by m dot and small w is W dot Cv by m dot. They are specific heat input and specific work output. Now this is the common assumptions for all the control volumes are each processes in the devices are in steady state. They are actually steady state and steady flow device. They are steady flow devices, and there is no changes in kinetic and potential energy. These are the common assumptions from the problem. Now the solution. I think you have understood the processes. Just once more. From 1 to 2 is the isentropic compression. After the evaporation process is over, in the evaporation process, heat is absorbed from the refrigerated space and thereby the cold space is created or it is maintained. Now, after that, by compression, it is raised to the pressure P2 so that heat can be rejected in the atmosphere at a higher temperature. So this is the compression from 1 to 2. Then from 2 to 3, it will be in the condenser. The condenser, there will be phase change, and the heat will be rejected to the atmosphere. Now from 3 to 4, there will be pressure drop, and that is achieved by an expansion valve or capillary tube. Now we know that if we write the first law across this expansion valve or capillary tube, there is no heat input or heat interaction, there is no work interaction, and we assume that kinetic energy and potential energy changes to be zero. So if we write the first law for the expansion valve or capillary tube, it will be Q plus H I plus Vi square by 2 plus Gzi equal to He plus V square by 2 plus Gze plus small w. Now for this device, we know that there is no change in kinetic energy, no change in potential energy. This device has no heat interaction and no work interaction. Therefore, the first law or the energy conservation gives Hi equals to He. That is, the enthalpy at the inlet is equal to the enthalpy at the exit. So for an expansion valve or capillary tube, the process is also known as throttling process. For a throttling process, the enthalpy at the inlet and enthalpy at the exit, they are same. So for this process from 3 to 4, the enthalpy at 3 equals to enthalpy at 4. Sometimes we loosely call it isenthalpic process, but you have to note that the end state enthalpies are same or equal, but we do not know anything about the enthalpy values in the intermediate points. Therefore, it will be too crude to call it an isenthalpic process. Simply from the first law point of view, the end state enthalpies are same, because in between or the intermediate states are very much unstable, or you may call the they are in non-equilibrium condition. That is why we do not know exactly the conditions or the state of the intermediate points. Simply we can use this for the analysis. Therefore, we have to keep in mind that end state enthalpies for the throttling process are same. Now, let us see the solution strategies. Now, the control volume, we will analyze one by one all the control volumes what are necessary for the calculation of the desired quantities. Here, one control volume is compressor. The first control volume that we will analyze is compressor. The inlet state is known, the compressor inlet state, that is T1. If we compare always the inlet condition, it is given 20° centigrade temperature, this is given minus 20° centigrade, and condenser temperature is given as 40° centigrade. So At this point, this temperature is minus 20 degrees centigrade, and this temperature is 40 degrees centigrade. So this point is known. This is saturated vapor at minus 20 degrees centigrade. So state 1 is completely known. For state 2, the entropy is same as S1 because 1 to 2 is isentropic process, and the pressure here is also known because this is a constant pressure process. The pressure here can be determined because temperature is given. So pressure here, that is P2, is nothing but P sat at 40 degrees centigrade. That is, P2 is nothing but the saturation pressure at 40 degrees centigrade, because this is a saturation line and pressure everywhere from 3 to 2, they are same. Therefore, this pressure is saturation pressure at 40 degrees centigrade, and that is same as P2. Therefore, at point 2, the entropy value is known and the pressure is known. At point 3, this is saturated liquid at 40 degrees centigrade. This point is on the saturated liquid line at 40 degrees centigrade. Therefore, H3 can be calculated as HF at 40 degree centigrade, and H4 here is same as H3 as we have seen earlier for throttling process. The end state enthalpies are same. So once H3 is known, H4 can be determined. Now we will see these calculations step by step. Now first, the control volume is the compressor. The inlet condition known, T1 known, minus 20 degrees centigrade, and it is saturated vapor. So state is fixed or known. Exit state, that is the end of the isentropic compression. P2 is known, that is saturation pressure at T3. And we will analyze, we will see that from energy equation for the compressor, it is H2 minus H1, because if we compare with the first law and we consider that there is no kinetic energy and potential energy change, then we can write that Hi equal to He plus W. There is no heat interaction because this is isentropic process or adiabatic reversible process, so this is 0. So W is equal to Hi minus He. It will be H1 minus H2. I is the inlet, so inlet is 1, state 1, and E is exit, so this is state 2. Now, since this is conventionally, this is work output, so work input to the compressor is negative of that, so it will be so that is H2 minus H1. We know that this is isentropic process, therefore S2 equals to S1, that I have already told. So for state 2, pressure is known and entropy value S2 is known. Therefore, state 2 is also known. P2 and S2 are known. Now, next, how to calculate the value of H2 at state 2. The temperature at point 3, if we recall the thermodynamic diagram, is like this. So this is 1, this is 2, this is 3. Temperature here is T3, T3 is known. P2 is same as the saturation pressure at this point. So this is from the steam table or the temperature based steam table of the refrigerant R134A. We can calculate the value of pressure or the saturation pressure, that you can see in the saturation table of R134A. This is temperature based because you see that temperature is the independent variable given, that is the leftmost column. Now corresponding to 40 degrees centigrade, you can see that the pressure is given as 1017 and the unit is kilopascal. It is mentioned here, unit is kilopascal. So the saturation pressure corresponding to 40 degrees centigrade is seen from the steam table to be 1017 kilopascal. Therefore, it is 1017 kilopascal, and this value is corresponding to H1 is nothing but Hg, that is specific enthalpy of the saturated vapor at 40 degrees centigrade. I'm sorry, this will be at minus 20 degrees centigrade, and this S1 is the specific entropy of the saturated vapor at minus 20 degrees centigrade. You can see that, you can verify that. You see that corresponding to minus 20 degrees centigrade, the Hg value and the Sg value. This is 386.08 kilojoule per kg, and this is 1.7395 kilojoule per kg Kelvin. So corresponding to minus 20 degrees centigrade, the saturated vapor enthalpy and saturated vapor entropy can be seen. So we have note these values here: 386.1 kilojoule per kg and 1.7395 kilojoule per kg Kelvin. So S2, we know that S2 equals to S1, the same value. Now by linear interpolation in the R134A table, we can determine the value of H2, because you see that corresponding to point 2, the entropy value is known and the pressure value is known, but the enthalpy value H2 is not known. So how to calculate the value? This is in the superheated vapor table. We can verify that also. If we know the entropy value S2 value is 1.7395, and since this is isentropic process from a lower pressure, it must be in the superheated vapor, but still we can verify from the value of Sg at 40 degrees centigrade. The entropy value for the saturated vapor is 1.7123 at 40 degrees centigrade, but S2 value, we have seen that it is 1.7395. Therefore S2 is greater than Sg at 40 degrees centigrade. Therefore state 2 is superheated. Vapor. State 2 is superheated vapor. Now how to calculate the value of enthalpy at state 2? This will be done by linear interpolation. Now we will see that. How that is done? Please follow that. What we have to do is we have to calculate the enthalpy value, that is H2, corresponding to 1017 kilopascal, that is P2, and 1.732 7395 kilojoule per kg Kelvin, that is S2. Now, how to calculate that? You see, in the superheated table for R134A, a pressure given, the data corresponding to 1000 kilopascal is given, and the next data is given corresponding to 1200 kilopascal. No data is given corresponding to 1017 kilopascal. So what we have to do is we have to assume that the values of enthalpy and all other properties are linearly varying between 1000 kilopascal and 1200 kilopascal. So you see that now we have located the pressure values. So this 1017 kilopascal is located between 1000 and 1200. This value is between 1000 kilopascal and 1200 kilopascal. Now what we have to do is we have to locate this value of entropy. You see that in the 1000 kilopascal range, or in the table of 1000 kilopascal corresponding to 40 degree centigrade and 50 degree centigrade, the entropies are 1.7148 and 1.7494, and you see that this value 7395 is in between. Therefore, in 1000 kilopascal or at 1000 kilopascal corresponding to 1.7395 entropy, the value will be in between 40 and 50, and the corresponding enthalpy values are also given. So for this entropy value, the enthalpy value is this at 1000 kilopascal. For this entropy value, the enthalpy value is this at 1000 kilopascal. Therefore, our aim is to determine what is the enthalpy value in between, where the entropy value is this much. That we can see by constructing one table like this. So what we will do is we will construct a table like this. We will have 4 columns. Now here we will write entropy value, and here we will write enthalpy value corresponding units kilojoule per kg Kelvin. Here the unit is kilojoule per kg. Here we will write corresponding to 40 degrees centigrade, and here we will write corresponding to 50 degrees centigrade. The entropy value corresponding to 40 degrees centigrade, and for all these values the pressure is 1000 kilopascal. So at 1000 kilopascal, 40 degrees centigrade, in the superheated vapor table, the entropy value is 1.7148, and corresponding enthalpy value is 420.8. 0.25. Corresponding to 50 degrees centigrade, the entropy value is 1.7494, and corresponding enthalpy value is 431.24. Now this entropy is known, that is S2. So this is 7395. The aim of the linear interpolation is to calculate what is the missing value here. That means what we are trying to do is we are trying to fit a line where this is one point, this is another point, this is say entropy axis, this is say enthalpy axis, this is corresponding to say 40 degrees centigrade, and this is corresponding to say 50 degrees centigrade. We assume that there is a straight line from this to this. Now you see that the corresponding enthalpy values at 40 degrees centigrade and 50 degrees centigrade, they are known. Similarly, the entropy values are also known. So here we can see that this is 40 degrees centigrade. So this is this. This is 50 degrees centigrade. This is this. Corresponding enthalpy values. This is this. And this is this. Now our aim is to determine the value of enthalpy for this value of entropy. This value is in between this and this. So this value will be somewhere here. Now if we draw a parallel line of the enthalpy axis, from this point, what is this? This is this. Now what we will do is, from this point we will draw a line which is parallel to the entropy axis, and this value you have to determine. So at this point we have to determine the value. Okay, so how to do that? We can construct the equation of a straight line considering this point and this point. Since both the entropy value and the enthalpy values are known, so the equation is like S, say this is S2, this is say S1, this is say H1, this is say H2, and this is S, and this is H. So we can write in a similar to that of the equation of a straight line in terms of x and y. That is x minus x1 by x2 minus x1 equals to y minus y1 by y2 minus y1. Now what we have to do is we have to replace x by h and y by s. So it will be s minus s1 divided by s2 minus s1 equal to h, sorry, we told that we will replace x by h, so it will be h minus h1 divided by h2 minus h1 equal to s minus s1 s2 minus s1. Now we note that the right hand side is completely known because all the values are known. S, S1, S2, all the values are known. On the left hand side, H1 and H2 are known, H is unknown. So this is one equation and we can determine a single unknown H. It will be simply H1 plus H2 minus H1 multiplied by this term. That is S minus S1 divided by S2 minus S1. Okay, so for linear interpolation, I always suggest you to construct such a table where on the top, that is on the top column, the topmost column, you write the variable which you know completely, and on the lower row, you write the variable for which you only know the endpoints. You have to determine this value. Now this value can be determined to be 428.09. So I hope this interpolation process is clear to you. Now let us go back to the main discussion part. The same thing can be done for a pressure of 1200 kilopascal. So what we have seen is we have calculated the entropy value, calculated the enthalpy value corresponding to the entropy value of 1.7395. That was calculated to be 428.09. Similar calculation is to be done at 1200 kilopascal because entropy value which is to be matched is 1.7395, but here none of these are exactly matching with 7395, so we have to again interpolate. You see that corresponding to 50 degrees centigrade, the entropy value is 1.7237, which is lower than 1.7395, and at 60 degrees centigrade the entropy value is 1.7584, which is greater than or more than this value. Therefore, corresponding to this entropy value, the other property values will lie in between. So again we have to interpolate the same way, and now we can again construct the similar table for 1200 kilopascal. At 1200 kilopascal, we will construct the table. that will have 4 rows and 2 columns. On the top you have entropy, on the lower row you have enthalpy. This is now 50 degrees centigrade and this is now 60 degrees centigrade, because we have seen that at 1200 kilopascal the entropy values, it is 1.7395, is coming in between 50 and 60 degrees centigrade. Therefore we have to interpolate between the 50 and 60 degrees centigrade values. The corresponding values can be noted as 1.7237 and here it is 1.57584. The values I have noted from the table, and corresponding values of the enthalpy are 426.84 and 438.21. Here the entropy value, that is 7395, same as this. Corresponding enthalpy values we have to determine the same way as earlier. So we can write the equation of the straight line and accordingly we can calculate the value calculated to be 432.02 kilojoule per kg. Now we go back to the main part. So what we have done is we have calculated the enthalpy values here, that is 428.09 and here it is 432.02 and the corresponding entropy values are 1.7395, same value 1.7395. Now what we have to see is this enthalpy value is corresponding to this entropy value and this pressure value, but in our problem the pressure value is P2 is how much? 1017 kilopascal. So we have to therefore determine the enthalpy value, that is H2 at P2 and S2. That S2 value is this one, but this P2 is not 1000 kilopascal. Neither that P2 value is 1200 kilopascal. Therefore again we have to interpolate between 1200 kilopascal and 1000 kilopascal, keeping the pivotal point as entropy. That means so far what we have done is we have written the table as at some pressure and correspondingly we varied enthalpy with entropy. In the earlier case we have written entropy here, enthalpy here. Corresponding values we have noted from the table. Now for the interpolation between this and this, what we have to do is we have to write at entropy value S2 equals to 1.7395. We will construct a table like this, where again there will be 4 columns. Now in these columns, now there will be pressure instead of entropy. So here will be pressure, here will be enthalpy. So here pressure is known. First pressure is 1000. The last pressure is 1200. Corresponding enthalpy value at 1000 we have noted 428.09. 428.09. At 1200 kilopascal, the enthalpy value is 432.02. And here the pressure at which the enthalpy value to be determined is 1017. Corresponding enthalpy value we can determine in the same logic by linear interpolation. That value is coming to be 428.42 kilojoule per kg. Here I have shown the linear interpolation mathematically. Here you see that at 1000 kilopascal I have written the linear equation, that is enthalpy at 1000 kilopascal some T prime degree centigrade. T prime is in between 40 and 50, and corresponding entropy values we have written. This T prime is not known. Please note that this T prime is not known. It is in between 40 degree and 50 degree centigrade. We can determine in the same way, just by replacing H with T, we can determine what is the value of T prime. But in this problem, we need not calculate T prime. So simply we will calculate enthalpy only. So I think this is clear. I have just written in the mathematical form. So this is 428.09 kilojoule per kg that we have already calculated earlier. Now at 1200 kilopascal, this is enthalpy at 1200 kilopascal. Now this is T double prime. Remember that T double prime is again different from T prime because T prime is between 40 degree and 50 degree centigrade. But this T double prime is between 60 degree centigrade and 50 degree centigrade. So this T double prime and T prime, they are different. Now here it is enthalpy at 1200 kilopascal T double prime degree centigrade minus enthalpy at 1200 kilopascal 50 degree centigrade. 50 degree centigrade is the lower temperature and 60 degree centigrade is the higher temperature. So we are basically interpolating between 50 degree and 60 degree centigrade to determine the enthalpy value corresponding to the entropy value which is known for S2, that is 1.7395. The same, following the same logic, we calculate this enthalpy at 1200 kilopascal and T double prime degree centigrade to be 432.02 kilojoule per kg that we have already calculated. Now here we are doing what? This, the last calculation that we have done by pivoting S2 equals to 1.7395 kilojoule per kg Kelvin. Here we are varying enthalpy with pressure. So this is the pressure at which the enthalpy value to be calculated is this. Corresponding to 1000, the enthalpy value is this. Corresponding to 1200, the enthalpy value is this. So this is, you see, this is this and this is this. So we have just replaced these values to calculate what is the value of enthalpy. You see that what is the value of enthalpy at 1017 kilopascal and T degree centigrade. Now T degree centigrade, how to calculate T degree centigrade? T will be in between T prime and T double prime. That is not needed. Only H at 1017 kilopascal and T degree centigrade is 428.42 kilojoule per kg. That is nothing but H2. Okay. You see that here we have calculated by linear interpolation the value of H2 to be 428.42 kilojoule per kg, and we know H2, we know H1, therefore we can calculate what is the compressor work input, that is 428.4 minus 386.1. 386.1 is this one, that is the inlet to the compressor, 1 to 2 inlet to the compressor, there is H1, and at the exit to the exit from the compressor, this is H2. H2 is this one, so we can calculate compressor work input per unit mass of the working fluid. So we have seen the analysis of the compressor. Now we will try to see the analysis of another control volume, that is the expansion valve. For the expansion valve, the temperature T3 is known. It is given as 40 degrees centigrade. Saturated liquid, so we can determine what is H3. H3 I have already told, this is H3 is HF at 40 degrees centigrade, and that we can see from the table. That we can see from the table, we see that is H3 HF at 40 degrees centigrade. HF at 40 degrees centigrade is at 40 degrees centigrade. HF value is this one, 256.54. So this is 256.54. You see that is 256.5 written. And H4 is H3, as we know, that is enthalpy values at the extreme points for the throttling process, they are same. So H4 is also known. The analysis we have written for the expansion valve, H3 is H4, and entropy equation we have written, but for this problem this is not needed. Simply we have shown the entropy balance, that is entropy increases because this throttling process is an irreversible process. So entropy increases from 3 to 4. That we have shown is S3, S4 is S3 plus Sgen, and we know that Sgen is always positive. So S4 is greater than S3. Now the next control volume is the evaporator. Evaporator is the component where the heat absorption takes place. The end state 4, the temperature is known. The temperature is known. What is the temperature? Minus 20 degrees centigrade, evaporator temperature, and enthalpy value is also known. Exit state, state 1, it is known. It is saturated vapor at minus 20 degrees centigrade. Now we can analyze by energy equation, that is heat absorbed is H1 minus H4. That is the final enthalpy minus the initial enthalpy. For this is the heat absorption process. Now by absorbing heat, its energy increases from 4 to 1. So what is the heat supplied? This is heat supplied is final enthalpy minus the initial enthalpy. This is H1 minus H4. We know H1, we know H4, therefore we can calculate what is the enthalpy difference, and that is QL. Now we know that COP is defined as the heat absorbed divided by the work input to the compressor. So heat absorbed we have calculated earlier in the previous page, 42.3 kilojoule per kg, and this is calculated just now, it is 129.6 kilojoule per kg. So the COP value is coming to be 3.064. Now what is the refrigeration capacity? Refrigeration capacity of a refrigerator is m dot into H1 minus H4. H1 minus H4 means in the evaporator process, the heat absorbed per unit mass is H1 minus H4 that we have just seen. Multiply this with the mass flow rate, we will get the total refrigeration capacity. That is an extensive property. So this is m dot into H1 minus H4. M dot, we know that it is 0.03 kg per second, and this we have just calculated to be 129.6 kilojoule per kg. So the final answer, that is the refrigeration capacity, is 3.89 kilowatt. So this is the end of the solution of the problem that is given. Thank you.